Around 2000, Union Pacific placed the largest single locomotive order in North American history, over 1,000 units from EMD. Everyone used DC traction, technology the rest of the industry had already written off. BNSF, CSX, and CN were all moving to AC power. The new motors promised better adhesion, fewer burnouts, and the ability to replace 5 older locomotives with 3. It was supposed to be the future, and Union Pacific, the biggest railroad on the continent, wanted none of it. This was the order that made no sense unless you understand how railroads actually make money. In May 2000, Union Pacific formalized this controversial stance with an official announcement that stunned the industry: a firm order for 1,000 brand new Electromotive Division SD-70EM locomotives. This wasn't just a routine fleet refresh, it was a massive capital commitment that quickly ballooned. By the time the final unit rolled off the production line in February 2005, the purchase had expanded to 1,427 locomotives. To put that in perspective, this remains the largest single-model locomotive purchase in the history of North American railroading. A single carrier had committed billions of dollars to a solitary design. But the real shockwave wasn't the price tag or the historic volume. It was the engineering specification. Every single one of these 1,427 units was built with traditional, direct current traction motors. While competitors like Burlington Northern had spent 7 years establishing alternating current traction as the gold standard for heavy haulage, Union Pacific went in the exact opposite direction. They doubled down on the very technology their rivals were actively retiring. This wasn't a tentative experiment or a temporary stopgap. It was a structural, long-term bet on direct current power at a scale never seen before or since. On paper, the decision looked like a massive step backward, a stubborn refusal to embrace modern, highly efficient technology. But Union Pacific wasn't acting on blind sentiment. Behind the scenes, the railroad was operating under a completely different set of economic and operational pressures, making a high-stakes play that perfectly aligned with its own corporate strategy. By the late 1990s, a geographic and technological divide split the North American rail network. Burlington Northern's pioneering 1993 order of EMD SD-70 Max had proven that alternating current traction was no longer an experimental gamble. It was a highly profitable reality. In the years that followed, Burlington Northern's successor, BNSF, rapidly built up its alternating current fleet to haul heavy coal out of the Powder River Basin. CSX soon followed, buying up GE AC 4400 CWs to conquer the steep grades of the Appalachian coal country. Even Conrail and Canadian National joined the transition, using the immense pulling power of alternating current locomotives for their own heavy haul and high tonnage routes. To the rest of the industry, the physics-based math was settled. Alternating current traction allowed 3 locomotives to do the work of 5 older direct current units, dramatically cutting fuel, maintenance, and crew costs. Operating ratios improved, and profitability climbed. Yet, as the Continental Rail network aligned behind this new standard, Union Pacific stood alone as the major holdout. This divergence created a stark industry contradiction. On one side of the ledger stood every other major Class I carrier, investing heavily in the expensive, high-adhesion future of alternating current because they believed it was the only way to remain competitive. On the other side stood Union Pacific, buying traditional direct current power at an unprecedented scale. It was a decision that defied the accepted engineering consensus of the era, raising a fundamental question about how a railroad measures value, manages its network, and ultimately generates profit. The pressure on Union Pacific to conform was driven by a ruthless manufacturing duopoly. In the early 1990s, the North American locomotive market belonged almost exclusively to 2 corporate titans: General Motors' Electromotive Division, or EMD, and General Electric. For decades, these giants had competed on raw horsepower and mechanical reliability. But by 1993, the battleground shifted entirely to traction technology. Burlington Northern drove this shift, acting as the launch customer for EMD's new SD70 MAC. This massive commitment to AC traction units transformed coal operations in the Powder River Basin, demonstrating to Wall Street and rival executives that alternating current was a highly profitable reality. The SD70M MAC became the definitive proof case, establishing that a railroad could run fewer locomotives to move heavier tonnage. General Electric responded immediately. In 1994, GE rolled out the AC4400CW, an aggressive competitor designed to strip market share from EMD. GE produced these locomotives quickly, offering shorter lead times that allowed major carriers to overhaul their fleets. This intense rivalry sparked an industry-wide technology race, as both builders marketed AC traction as the primary driver of operational efficiency. Railroads rushed to place orders, desperate to secure their competitive edge. EMD and GE had successfully redefined the standard of modern railroading. For Union Pacific to reject this transition meant actively resisting the combined industrial momentum of the two most powerful manufacturers on Earth. To understand why the rest of the industry viewed Union Pacific's massive DC purchase as a step backward, one must look at the physics of how a locomotive grips the steel rails. For over half a century, diesel-electric locomotives relied on direct current traction motors. These DC motors used physical carbon brushes and commutators to transfer electrical current to the axles. Under heavy loads or at low speeds, this mechanical contact created immense friction and heat. If a heavy train slowed down on a steep grade, DC motors would rapidly overheat, risking catastrophic burnout. To prevent this, engineers had to keep their trains moving above a minimum continuous speed, typically around 11 miles per hour, or risk melting the motor windings. Alternating current traction changed the physical limits of railroading. Instead of brushes, AC motors used three-phase induction, relying on rotating magnetic fields generated by computerized inverters. This eliminated the primary mechanical wear point inside the motor. More importantly, it allowed for precise, real-time control of wheel slip. Where traditional DC locomotives achieved about 27% adhesion before the wheels began to spin, AC traction units routinely reached up to 45% adhesion, a near doubling of usable grip. In late 1992, testing at the Transportation Technology Center in Colorado quantified the real-world impact of this physical advantage. The data demonstrated that 3 AC locomotives could perform the exact same work as 5 comparable DC units. This 3-for-5 ratio redefined the economics of heavy-haul railroading, because a central computer could constantly adjust the electrical frequency and voltage to each axle individually. AC locomotives could lug heavy trains at crawl speeds of just 2 miles per hour indefinitely. There was no risk of motor damage, even under maximum load. On descending grades, these same power electronics provided continuous, high-energy dynamic braking down to a near standstill. For railroads moving millions of tons of freight, the technology offered a clear path to running longer, heavier trains with fewer locomotives, fewer crews, and significantly less downtime. In late 1993, Burlington Northern transformed the theoretical promise of alternating current into an undeniable operational reality. The railroad became the launch customer for EMD's newly developed SD70 MAC, taking delivery of Unit 9400 in November. Over the next 3 years, Burlington Northern expanded this program into a massive fleet of 350 locomotives, numbered from 9,400 to 9,749. This was not a tentative trial. It was a bold, systematic deployment designed to conquer the brutal grades of the Powder River Basin. As these heavy-haul units began moving million-ton coal shipments out of Wyoming, the entire railroad industry watched the performance data. The results were definitive. On steep mountain passes where older direct current motors frequently overheated and burned out under heavy loads, the SD70 Max lugged maximum tonnage trains at crawl speeds of just a few miles per hour, indefinitely and without damage. This vast, highly visible fleet served as a public proof case that Wall Street and rival executives analyzed closely. Almost overnight, AC traction became synonymous with modern heavy-haul efficiency. The North American locomotive market responded immediately, shifting its baseline expectations. By the late 1990s, buyers and builders alike began treating AC traction as the standard for any high-horsepower road locomotive. The industry consensus had solidified, creating immense peer pressure. To buy anything else for heavy freight operations looked less like financial prudence and more like a stubborn refusal to modernize. Union Pacific was the largest, wealthiest railroad in North America. Following its acquisitions in the 1980s and the 1990s, the company possessed the massive capital reserves required to absorb the premium price of AC technology. Financially, Union Pacific was better positioned than any other Class I carrier to lead the industry-wide transition. Yet, as competitors signed massive contracts for AC units, Union Pacific repeatedly said no. This resistance was not a temporary delay or a brief pause to watch the technology mature. It was a systematic, deliberate refusal that persisted for nearly 10 years. Year after year, while Burlington Northern, CSX, and Conrail built up their AC rosters, Union Pacific's purchasing agents consistently specified direct current locomotives for their core freight orders. Even when General Electric and EMD offered standardized AC designs directly from their catalogs, Union Pacific rejected them in favor of traditional, brush-equipped DC models. To outside observers and Wall Street analysts, the strategy appeared entirely counterintuitive. The physical superiority of a C-traction was no longer an engineering theory. It was a proven operational reality generating high returns on rival networks. Union Pacific's persistent rejection of this consensus reframed the entire debate. This was no longer a question of electrical engineering or traction physics. It was a fundamental disagreement in corporate strategy, revealing a stark institutional divide over how a modern railroad should manage its assets, allocate its capital, and ultimately generate profit. To many industry analysts and rival executives, Union Pacific's massive commitment to direct current locomotives looked like a clear case of corporate malpractice. The math seemed indisputable. By refusing to adopt alternating current technology, the railroad was leaving millions of dollars of fuel savings and maintenance efficiency on the table. How could the industry giant be so blind to a technology that was already proving its worth every day on the tracks of its fiercest competitors? While Burlington Northern and CSX extracted massive productivity gains from their new AC fleets, running 3 locomotives where they once needed 5, Union Pacific was still buying traditional motor designs. To the outside world, this was the order that made no sense. It looked like short-term thinking disguised as fiscal discipline. Wall Street analysts openly questioned whether Union Pacific's leadership was simply too cheap, too conservative, or too stubborn to invest in the future. Critics argued that the railroad was missing out on the core drivers of modern network efficiency, falling behind in the race for superior asset utilization. By sticking with DC traction, the railroad was saddling itself with high maintenance costs, frequent motor burnouts, and bloated train crews. Every other Class Y railroad was moving toward a high-adhesion future, while the largest carrier on the continent seemed stuck in the past. This stark contradiction created a powerful narrative. Union Pacific was falling behind, paralyzed by a culture of caution that prioritized low upfront costs over long-term profitability. It was a highly persuasive indictment, and on the surface, the evidence against Union Pacific's strategy seemed completely overwhelming. To understand why Union Pacific resisted the industry-wide rush to alternating current traction, one must look past the engineering lab and examine the corporate ledger. For Union Pacific's executive leadership, the locomotive acquisition process was a cold, mathematical exercise in capital allocation, rather than a quest to field the most advanced machine on the market. At the turn of the millennium, alternating current locomotives commanded a steep premium. While precise purchase figures remained closely guarded corporate secrets, industry estimates placed the cost of AC traction units at 10 to 15% higher than their direct current equivalents. In the real world of corporate capital planning, every dollar spent on a premium feature was a dollar that could not be used to buy more physical assets. This price gap transformed locomotive procurement into a stark trade-off between quantity and capability. A fixed capital budget could either buy a smaller, high-performance fleet of AC locomotives or a significantly larger pool of proven DC units. Union Pacific's sprawling network, which had recently absorbed the massive Southern Pacific, was suffering from acute, systemic power shortages. The railroad required broad, system-wide coverage rather than specialized performance on a handful of mountain passes. Buying premium AC units meant leaving a massive deficit in total fleet coverage. By choosing the EMDSD-70M, Union Pacific stretched its capital to the limit. For the price of a smaller AC fleet, the railroad bought a massive army of 1,427 DC locomotives. It was a simple, pragmatic calculation. On a vast and congested network, a locomotive that is physically present and working will always generate more revenue than a technologically superior model that was never purchased. The physical advantages of alternating current are undeniable, but they are not universally useful. The technology's primary financial justification is highly dependent on speed. An alternating current motor's maximum performance edge is realized at crawl speeds, specifically around 10 miles per hour under heavy lugging conditions. This is where the computerized torque control prevents wheel slip and protects the electrical components from overheating. For Burlington Northern and its successor BNSF, this low-speed capability was a perfect match for their business model. Their network was anchored by heavy, slow coal unit trains, dragging millions of tons out of the Powder River Basin. In that specific operational profile, 3 alternating current locomotives could reliably replace 5 direct current units on steep grades, instantly justifying the higher purchase price. Union Pacific operated under a completely different structural reality. Its revenue base did not depend on low-speed coal drags. Instead, Union Pacific's network was optimized for high-speed, long-distance intermodal containers and automotive hotshots. These priority trains did not crawl up mountain passes at 10 miles per hour. They cruised across the vast expanses of the overland route at 60 to 70 miles per hour. At high speeds, the physical limitations of traction motors change completely. Once a train is up to speed, adhesion is no longer the limiting factor and the risk of traction motor burnout disappears. In this high-speed environment, a direct current locomotive performs almost identically to an alternating current unit, but at a fraction of the initial capital cost. For Union Pacific's fast freight network, paying a premium for alternating current traction meant purchasing immense low-speed pulling capability that the railroad's actual traffic mix could never exploit. On their rails, the expensive computer-controlled inverters would spend most of their lives doing nothing. Locomotive purchasing is only the first step in a 30-year financial commitment. The true cost of any fleet is decided in the repair shops. Shop foremen at major facilities like North Platte, Nebraska, and Roseville, California, looked at alternating current locomotives with deep skepticism. While an alternating current motor has no physical brushes or commutators to wear out, the supporting systems introduced entirely new layers of technology. An alternating current locomotive relies on massive, computerized inverters, liquid cooling loops, and demanding software. These components brought failure modes completely alien to a traditional direct current fleet. Instead of routine mechanical wear, shop crews had to diagnose inverter cooling system failures, software bugs, and high-voltage electrical spikes. Maintaining these advanced machines required a completely different, expensive spare parts inventory and specialized diagnostic tools. It also demanded intensive technician retraining for shop forces accustomed to traditional electrical systems. For Union Pacific's mechanical department, a massive fleet of identical direct current SD70Ms represented simplicity. The parts were already in the warehouses, the mechanics already possessed the skills, and the failure modes were entirely predictable. Choosing direct current power allowed Union Pacific to avoid a parallel supply chain and a massive training program. This final pillar of the railroad's strategy kept maintenance predictable, protecting operating margins where they mattered most, in the daily reality of the shop floor. In 1996, Union Pacific finalized its acquisition of the Southern Pacific. Almost immediately, the monumental task of integrating two massive, distinct rail systems fractured under operational pressure. By July 1997, the merged network began to collapse into a historic service crisis. A study by the University of North Texas documented the devastating fallout: severe service disruptions, massive shipping delays, lost industrial production, and spiraling freight costs for businesses nationwide. The operational chaos was further compounded by more than a dozen major crashes and derailments across the system. With yards gridlocked and transit times doubling, Union Pacific faced an acute locomotive shortage. The railroad had to run every active locomotive in its fleet at maximum capacity just to keep basic freight moving. This operational emergency transformed UP's fleet planning strategy from a long-term economic debate into an immediate problem of system survival. Under these extreme conditions, the risk of introducing a highly complex, unproven technology was a gamble Union Pacific's leadership could not afford. Alternating current locomotives, with their computer-controlled inverters and specialized diagnostic needs, represented an operational variable that could paralyze already strained maintenance shops. If an AC locomotive suffered a software glitch or an inverter failure, it required specialized technicians and tools that simply did not exist in many former Southern Pacific facilities. By contrast, direct current locomotives were highly predictable. Every mechanic on the payroll knew how to swap a traction motor brush or troubleshoot a DC electrical cabinet. Choosing the simpler, proven DC platform stretched capital further and injected much-needed stability into a bleeding network. When a railroad is fighting to keep its main lines open, the unglamorous reliability of direct current power looks far safer than the sophisticated promise of alternating current. In May 1997, Union Pacific took delivery of Locomotive 8152, the first of a new class of power designed to prove the ultimate potential of alternating current. This was the EMDSD 9043MAC, a massive machine built on an exceptionally long 6-axle frame. It was part of an industry push toward a monstrous 6,000 horsepower single-engine AC locomotive. EMD marketed this platform as the future of heavy haulage, promising to consolidate more power into fewer units. Because the high horsepower H engine was not yet ready, these early versions were equipped with a standard 4,300 horsepower 710 engine, but they retained the heavy frame and complex AC electronics of the flagship design. For Union Pacific, this field test program was supposed to be a gateway to high horsepower AC performance. Instead, it became an operational nightmare. The massive physical size of the locomotives introduced severe structural flaws. Under the punishing weight of heavy freight service, the long steel frames began to crack. Inspectors traced the failures to a basic assembly error: improper torque on the fuel tank mounting bolts. This mechanical flaw prevented the massive fuel tank from floating as designed, transferring extreme cyclic stress directly into the frame. Meanwhile, the advanced electronic systems buckled under daily use. Crews reported frequent traction inverter failures, erratic computer diagnostics, and rough riding qualities. The specialized computer hardware struggled with high-voltage spikes, causing the traction motors to trip and shut down on the main line. Union Pacific mechanical departments found themselves spending excessive shop hours chasing software bugs and electrical gremlins. The railroad ultimately labeled the entire program a failure, sidelining the units in storage yards like Missouri Valley, Iowa. The SD9043M AC experience confirmed the worst fears of UP's engineering department. A C technology was still immature, temperamental, and unproven. The math of railroading eventually forced a reckoning. By 2005, the operational environment had shifted too far to ignore. Train lengths grew, fuel prices spiked, and new emissions regulations took effect. The massive fleet of DC traction SD70Ms, once the bedrock of Union Pacific's recovery, could no longer shield the railroad from the physical realities of modern freight hauling. Union Pacific broke its long-standing resistance. The railroad placed its first major orders for alternating current power, acquiring hundreds of General Electric ES44ACs and Locomotive SD70AC locomotives between 2005 and 2015. This was not a tentative trial. It was a wholesale adoption. On heavy haul corridors across the West, the new AC units proved their worth, delivering the low-speed pulling power and high-adhesion reliability that UP had spent a decade avoiding. But the shift went further than buying new locomotives. Union Pacific later launched a massive capitalization program to convert its existing DC fleet. Partnering with Wabtec, the railroad committed over $1 billion to rebuild hundreds of older DC locomotives, stripping out the legacy electronics and retrofitting them with modern AC traction systems. The holdout had become an active adopter, proving that even the largest railroad must adapt when the economics demand it. The sudden pivot was not a confession of past ignorance, nor was it a sudden revelation that alternating current had magically become superior. It was a cold calculation driven by a changing network. By 2005, the physical work demanded of Union Pacific's fleet had fundamentally shifted. Train lengths grew longer, and total tonnage increased, pushing the limits of what direct current motors could drag without overheating. The operating environment itself at last made alternating current traction the better fit. Consolidating freight into massive, mile-long cuts of containers required immense, low-speed tractive effort to start and keep moving. At the same time, federal regulatory pressures closed the door on older locomotive designs. New Environmental Protection Agency Tier 2 emission standards took effect in 2005, forcing manufacturers to introduce advanced models like the EMD SD70AC and General Electric's ES44AC. These units integrated compliance with mature, reliable alternating current systems. Union Pacific did not change its taste in technology. It simply changed its tool when the weight of its trains made the old math impossible. The railroad's network realities had at last caught up with the physics of alternating current. Today, as Class 1s push toward next-generation propulsion, the lesson of Union Pacific's great gamble remains vital. Technology is never superior in a vacuum. A railroad's true efficiency is not defined by raw tractive effort, but by how precisely its fleet matches its specific network and traffic mix. In the high-stakes world of heavy rail, the ultimate machine is always the one that maximizes the bottom line. What do you think of Union Pacific's strategy? Let us know in the comments.